the steel deck pitched beneath Lieutenant Commander Joseph T. O'Callaghan's feet as dawn broke over the Pacific on March 19, 1945, 50 miles off the coast of Honshu, Japan. Flight crews hurried across the carrier's surface, preparing aircraft for the morning strike. The Catholic chaplain had risen well before sunrise, celebrating Mass for the early watch in the ship's dimly lit wardroom. Now, as light flooded across the water, he stood watching ordnance men maneuver the enormous tiny Tim rockets onto Corsair fighters lined up for launch. Each 11-foot weapon carried 500 pounds of high explosive, enough destructive force to tear through a battleship's thick armor plating. The Navy had never unleashed these experimental rockets in combat before today. Franklin would become the first carrier to use them against the Japanese homeland. What Father O'Callaghan couldn't possibly know was that within the next 3 hours, his ship would transform into a raging inferno that defied all calculations of destruction. USS Franklin would absorb damage so catastrophic that naval architects had insisted no carrier could survive it more than minutes. The ship would lose 807 men in the explosion's first moments, more casualties than any American warship had ever endured and lived. Her flight deck would become a nightmarish realm of burning ammunition and rockets, her hangar deck a furnace where temperatures climbed toward 2,000 degrees Fahrenheit. Yet she would remain afloat, against every principle of naval warfare, defying all expectations from material science. She would survive. And the reason for that survival had been engineered into her structure 5 years earlier in a Virginia shipyard by men told their innovations would never work. The morning of March 19th had started like any other combat operation at the edge of Japanese territory. Task Force 58 had been striking targets near Kobe and around Honshu for 3 days, weakening Japanese defenses before the planned April 1st invasion of Okinawa. Franklin, sailing as part of Task Group 58.2 under Rear Admiral Ralph Davison, had ventured closer to Japan than any American carrier dared approach. At 50 miles from the coast, she sat squarely within the range of Japanese land-based aircraft. Captain Leslie E. Geras, commanding officer since November 1944, had steered his ship forward with aggressive determination. Some crew members muttered that Geras, nicknamed Custer for his bold tactics, was courting unnecessary danger, yet the mission demanded it. The nearer Franklin operated to Japan, the more bombing runs her planes could complete, the longer they could spend striking their targets. Franklin had sent her first wave of aircraft roaring off the deck at dawn, 12 Corsair fighters and 16 Avenger torpedo bombers heading toward airfields around Kobe. The second strike was already spotted on deck, ready to go. 31 aircraft sat with engines warming, propellers turning, pilots running final instrument checks. The flight deck moved like a precision dance of carefully managed danger. Ordnancemen had been wrestling the experimental tiny Tim rockets onto the aircraft, securing the massive weapons to their pylons. Aviation gasoline trucks had just finished topping off the fuel tanks. In the hangar deck below, 22 more aircraft waited in storage, 16 completely fueled, 5 carrying bombs and rockets for the upcoming launch cycle. It was the deadliest moment in carrier operations, when hundreds of tons of aviation fuel and weapons sat exposed across 2 decks simultaneously, when a single spark could unleash catastrophe. At 07:08 hours, a lone Yokosuka D-4Y Judy dive bomber pierced through the clouds at 2,500 feet. The ship's radar systems hadn't picked it up among the clutter of returning American planes. The combat air patrol, watching for threats from other directions, hadn't intercepted it. The anti-aircraft gun crews, tracking multiple radar contacts, had no opportunity to swivel their weapons before the Japanese pilot committed to his dive. His name would never be recorded. He had maybe 30 seconds from pushing the control stick forward until impact. In that half-minute, he released 2 550-pound bombs with stunning accuracy, then disappeared back into the clouds before anyone could draw a bead on him. He had accomplished what every Japanese pilot dreamed of achieving, a perfect strike against an American carrier. Whether he lived to report his success would never be known. The first bomb punched through the flight deck centerline, 15 feet forward of the island superstructure. It ripped through 3 inches of wooden deck planking like paper, then penetrated the steel beneath and detonated deep inside the hangar. The blast wave, moving at 26,000 feet per second, tore through packed aircraft like a giant's fist. Aviation fuel caught fire instantly, creating a fireball that consumed everything within 50 feet. The explosion sent the number 1 elevator, a 4-ton steel platform measuring 60 by 34 feet, rocketing skyward out of its shaft like a launched missile. It climbed 400 feet into the air, flipped end over end, then crashed back down onto the deck, shattering into fragments that sliced through aircraft and men. Secondary explosions rippled across the hangar as fuel tanks split open and weapons cooked off. The second bomb landed aft, in the middle of 31 aircraft, warming their engines for takeoff. It detonated on impact with the flight deck, creating instant devastation. 31 fuel tanks erupted in sequence, each explosion feeding the inferno that rolled across the deck like a wave of pure flame. Sailors on nearby ships later reported feeling their vessels shudder from the force of the blast. The shockwave knocked sailors flat on destroyers 1,000 yards distant. On Franklin's flight deck, pilots strapped in their cockpits had no escape. Some managed to unbuckle and throw themselves overboard into the ocean. Others burned alive where they sat, their final screams drowned beneath the roar of exploding fuel and ammunition. What happened in the next 30 seconds would determine whether Franklin lived or died. In the hangar deck where the first bomb had struck, fires spread with terrifying speed. Gasoline from ruptured fuel tanks streamed across the steel floor, searching for openings. It found the ventilation system. Within seconds, burning fuel vapors were being pumped throughout the ship by ventilation fans still running automatically. The intense heat ignited stored ammunition near the aircraft. 20mm rounds began cooking off, their red traces streaking through the smoke like deadly fireflies. 40mm shells exploded with grenade-like force, hurling shrapnel through the hangar. Men attempting to reach firefighting equipment were cut down by their own ordnance. Then the tiny TIM rockets began igniting. These weapons, each weighing 1,300 pounds, remained experimental. Nobody knew how they would behave burning inside a ship. The solid fuel motors were engineered to burn at 5,000 degrees Fahrenheit for 6 seconds, generating 50,000 pounds of thrust. When the first rocket ignited at 7:11, 3 minutes after the initial attack, its motor came alive with a shriek audible above the roar of fire and explosions. The 11-foot missile shot horizontally across the deck like a meteor trailing flame. It punched through the half-inch steel plates of the island's structure like tinfoil and detonated on the starboard side, showering the deck with molten metal and jagged fragments. More rockets followed, screaming in every direction, some plunging into the sea, others smashing through compartment walls, one slicing a gun crew in half before exploding into the ocean. Another rocketed the length of the flight deck and vanished over the bow. The flight deck became a death trap where men fell to fire, explosion, or the unpredictable paths of weapons designed for sinking enemy warships. Lieutenant Commander Stephen Jurica Jr., the ship's navigator, was in his sea cabin just below the bridge when the first bomb detonated. A 1913 Naval Academy graduate who had served as intelligence officer aboard USS Hornet during the Doolittle raid, Jurica recognized instantly what had happened. The distinctive double thump of bomb impacts, followed by rolling thunder of secondary explosions, told the whole story. He grabbed his life jacket and battle helmet and bolted for the bridge. What he witnessed topside would haunt him for decades. The aft two-thirds of the flight deck was a raging inferno. Aircraft exploded, some launching themselves into the ocean as their engines caught fire and screamed at full throttle, propellers howling. The wooden deck was burning, feeding the flames. Gaping holes opened where bombs and rockets had torn through, some large enough for a man to fall through. Men were burning, running, rolling, diving over the rails into the sea. The ship was already listing to starboard, tilting maybe 5 degrees and increasing by the second. Smoke boiled from hangar deck openings, so thick it obscured the back section of the ship. Every few seconds, another tiny TIM rocket ignited and screamed across the deck on an unpredictable path. Jurica began gathering dazed survivors and organizing them into damage control teams. The forward flight deck section remained relatively clear. If they could establish a firebreak, if they could prevent flames from spreading forward, they might preserve the bow section. The aft flight deck, where 31 aircraft had been arranged for launch, was already lost. Jurica faced one of the hardest decisions any officer must make. He ordered everyone to evacuate the aft flight deck. All available personnel would concentrate on saving the forward two-thirds of the ship. It meant abandoning wounded men behind. It meant allowing fires to burn that firefighters might have controlled. But it meant deploying critically limited resources where they could actually save the vessel. Deep in the engineering spaces, Lieutenant Junior Grade Donald Arthur Gary was standing watch as the engineering officer in the forward engine room when the bombs struck. A 1943 Naval Academy graduate who had joined Franklin less than 4 months earlier, Gary had lived through the October 30, 1944 kamikaze attack that had killed 56 men. He understood what carrier damage meant. He felt the ship convulse twice, felt shock waves transmitted through the hull, heard the immediate roar of secondary explosions cascading through the vessel. The engineering watch officers looked to him for direction. Gary's immediate goal was keeping the engines running. Franklin had been cruising at 25 knots, her 8 Babcock and Wilcox boilers pushing maximum steam through 4 turbines to turn the propeller shafts. Now explosions on the flight and hangar decks were sending violent shock waves through the entire structure. Fuel oil lines burst, steam lines fractured, and critically, the ventilation system began forcing smoke into the engine spaces. On a conventionally built ship, the engineering crew would have faced 2 options: abandon the machinery and lose all propulsion, or remain and succumb to the smoke. Gary saw another possibility. The exceptional compartmentalization engineered into Essex-class design meant the forward engine room could be sealed off from the rest of the ship. He ordered his crew to seal every ventilation duct immediately. Emergency breathing apparatus, normally used for damage control, portable air bottles, was broken out. The men would breathe from bottles while keeping watch. Gary then methodically assessed what remained functional. Of 8 boilers, 2 in the forward boiler room still operated. 3 of the 4 turbines could still turn the shafts. The electrical system was failing in sections as fires burned through cables, but generators in untouched compartments remained operational, and the electrical ring main allowed power to be redirected around damaged areas. Gary made the choice that would determine whether Franklin survived. Rather than abandon his post, he would maintain the engineering plant. As long as Franklin had power, she had hope. Power meant pumping systems for fighting fires. Power meant ventilation for damage control teams. Power meant steering capability. And ultimately, power meant the ability to move through the water. A ship that could drive herself forward had options. A dead ship had none. But his crew was suffocating. The smoke was overwhelming them. The portable air bottles were running out. Gary recalled something from his engineering studies and from the ship's specifications. The carbon dioxide system, designed to flood fuel compartments during fires, could theoretically be modified to provide pressurized breathing air. It was a theoretical solution never tested. The system was meant to pump CO2, which would kill them instantly. But if he could isolate the CO2 bottles and instead use high-pressure air bottles from the damage control equipment, he might convert it into a pressurized breathing system that would flood the engine room with clean air, forcing smoke out through sealed ventilation ducts. With his crew collapsing from oxygen deprivation, Gary began manually redirecting valves and piping, converting a fire suppression system into a life support system. His hands trembled from lack of oxygen as he worked. Finally, he opened the valve. High-pressure air surged into the space, the pressure gauge climbing as the sealed hatches held. Smoke began venting out through small gaps around the ventilation dampers. Within 2 minutes, the air had cleared enough to breathe. The forward engine spaces, sealed and pressurized, became an island of life in a ship filling with death. On the hangar deck, Father O'Callaghan had been knocked off his feet by the first explosion. The 43-year-old Jesuit priest, who before entering military service had taught physics and mathematics at Holy Cross College in Worcester, Massachusetts, found himself lying in burning gasoline. Flames consumed his uniform. He rolled, extinguishing them, then struggled upright. Around him, the hangar deck had transformed into an inferno. The hangar deck was essentially a massive steel box, 654 feet long and 70 feet wide, with a ceiling just 17 feet 6 inches high. Overhead, pipes, cables, and ventilation ducts created a maze. Now the entire space was filling with flame and smoke. Aircraft burned as their aluminum skins melted and dripped like candle wax. Ammunition exploded continuously, a rhythmic roar punctuated by the shriek of tiny TIM rockets. The heat became so intense that the 2.5-inch special treatment steel plates of the deck began glowing red in scattered spots. O'Callaghan understood what he was witnessing, though the implications seemed impossible. The hangar deck wasn't collapsing. The STS plates weren't warping or buckling, despite temperatures that should have liquefied ordinary steel. The fire, as horrific as it burned, remained largely confined to the hangar level. It wasn't penetrating down to the third deck below. The steel wasn't failing. The ship's structure was enduring. O'Callaghan, his white chaplain's helmet marked with a black cross, moved through the flames. He administered last rites to dying men. His voice cut through the chaos. Through this holy anointing, may the Lord in his love and mercy help you with the grace of the Holy Spirit. May the Lord who frees you from sins save you and raise you up. After speaking these words, he turned his attention to the immediate crisis unfolding around him. Survivors stood in shocked clusters, their faces blank, waiting for direction. O'Callaghan began assigning tasks with methodical precision. Former members of the Bucket Brigade received their orders first. Ammunition had to go overboard immediately, before the heat could trigger explosions that would spread like wildfire. Wounded personnel needed transport to the forward elevator, away from the spreading flames. The crew scrambled for hoses connected to the fire mains. The hangar sprinkler system lay in ruins, its pipes torn apart by flying shrapnel. But alternative options remained. 4 independent fire main systems could still function. Portable pumps could draw from each one. Men dragged heavy rubber hoses toward the roaring inferno. The heat made the hoses nearly unbearable to grip. They burned through leather gloves as though the material was tissue paper. Other crews worked frantically to shove burning aircraft through the hangar deck openings, using tractors to push flaming wreckage out through the enormous 60-foot doorways. O'Callaghan moved through temperatures that melted rubber on his shoe soles, directing operations with the calm authority of a professor working through an equation on a blackboard. Later, sailors would describe him as something from an old saga, a warrior priest who seemed untouched by fear. Yet years later, when interviewers asked about those moments, O'Callaghan admitted the truth. Terror consumed him every second. What sustained him was a single understanding that kept his legs moving. The ship was holding. Against all odds, despite fires that should have torn the vessel apart, despite explosions that should have snapped her spine, Franklin remained above water. If the ship could endure, so could he. Up on the bridge, Captain Garris was orchestrating the larger response. This 54-year-old officer had joined the Navy as a sailor during the First World War and climbed through the ranks to become a naval aviator and commanding officer. He grasped instantly how dire circumstances had become. Radio systems were gone, flames had severed them completely. The Combat Information Center had been obliterated. Radar units were failing one after another as fire consumed their electronic components. The ship was listing toward starboard, the angle growing worse by the minute, now approaching 10 degrees. Fires continued spreading despite every effort to contain them. Most troubling of all, damage control reports indicated flames burning in multiple compartments, stretching from the hangar deck down to the third deck. Franklin was consuming herself from within. Garris made his first of several decisions that would spark debate. He ordered all non-critical personnel to the upper decks and prepared contingencies for abandoning the vessel. Hundreds of men emerged from below decks, some bearing burn wounds, others injured, many simply overwhelmed with fear. They congregated on the forward flight deck and bow area away from the worst fires. Some went overboard without waiting for orders, preferring the ocean to the flames. Others were hurled into the water by successive explosions. Within 20 minutes of the initial strike, more than 800 men were in the sea, swimming away from the burning ship or gripping debris and rafts. The USS Pittsburgh, commanded by Captain John E. Gingrich, was positioned roughly 500 yards from Franklin's port side. Gingrich steered his cruiser to shelter Franklin from the Japanese mainland and began preparing towing equipment. By 07:30, just 22 minutes after impact, Pittsburgh had secured a steel cable to Franklin and commenced towing operations, dragging her away from enemy territory at 5 knots. The pace was agonizingly slow, but it represented motion and distance from danger. The USS Santa Fe, under the command of Captain Harold C. Fitz, executed a maneuver that demonstrated extraordinary courage. He positioned his 10,000-ton cruiser directly alongside the burning carrier. Starboard side pressed against starboard side to evacuate wounded personnel and those no longer needed in the fight. With fire erupting and explosions occurring almost continuously across Franklin, with the carrier tilting toward his vessel, Fitz held Santa Fe steady for more than an hour. As the two hulls ground together in the ocean swells, sailors made their way across the narrow gap from the carrier to the cruiser. The wounded came next, lowered carefully on stretchers. Santa Fe's rescue teams actually crossed onto Franklin itself to assist with moving injured personnel to the rail. When Santa Fe finally pulled away at 0900, she had taken 832 men to safety, including 103 who were wounded. Her white hull bore the scars, blackened from radiant heat, her superstructure dented from grinding contact with the larger vessel. Yet she had rescued 832 souls. At 0800, a full 2 hours after the attack, Franklin's situation appeared hopeless to anyone observing from the surrounding ships. Pittsburgh's tow was all that kept her from drifting toward the enemy coast. She was listing 13 degrees to starboard. Flames and thick smoke engulfed her forward sections. Explosions continued as ammunition ignited from residual heat. The forward elevator, ripped from its shaft, lay twisted across the deck like a broken toy. The after elevator had vanished completely, blown entirely from the ship. The flight deck contained gaping wounds, some spanning 20 feet across. Radio Tokyo, monitoring American transmissions, proclaimed that a large American carrier had been destroyed near Japan. Japanese submarines operating in the region received new orders to locate and sink the remaining wreck. Every sailor still aboard Franklin, every observer on nearby vessels, understood they were witnessing a death struggle. Carriers simply did not endure this degree of damage. Everyone knew this. Yet in the forward engine room, Donald Gary was performing something almost miraculous. Working alongside his engineering team, breathing pressurized air within their sealed compartment, Gary had coaxed steam pressure back into 2 of the forward boilers. 3 turbines were now running. The electrical system, cobbled together through emergency damage control cables, was supplying power to vital systems across the forward section. At 0800, Gary relayed his status to the bridge using a sound-powered telephone, the only communications link still functioning. Bridge, forward engine room here. I have steam on 2 boilers, 3 turbines operational. I can turn the shafts for about 2 knots. 2 knots represented almost nothing, barely faster than a walk, yet it was propulsion. When Captain Gaz received this report, he made his most critical decision. He commanded Pittsburgh to release the towing cable. Franklin would move under her own power. The decision left observers stunned. A carrier burning and exploding, dead in the water, simply could not generate way through the water. The notion seemed absurd, but Garris recognized something essential. A moving ship possessed options. A ship being towed had none. A ship generating her own power could turn, could push air across the deck to exhaust smoke and heat overboard, could rebalance through speed and rudder action. At 08:12, Franklin's enormous bronze propellers began their rotation. The engineering crew had re-established power to the starboard propulsion shafts. Moving at just 2 knots, the carrier began creeping away from the Japanese coast. It represented one of the most extraordinary moments in naval warfare. A carrier destined for the bottom was moving on her own power. The return of propulsion changed everything. Even modest movement created wind across the deck. The 25-knot breeze produced by the ship's motion helped push smoke and heat away, instead of channeling them down into the vessel. The improved ventilation enabled damage control teams to operate more effectively. The starboard list gradually decreased as engineers carefully managed counter-flooding, intentionally introducing seawater to port compartments to balance the massive quantities of water that had accumulated on the starboard side from intensive firefighting. Most significantly, the ship's ability to move restored morale. Personnel who had been preparing to leave their posts returned to work. If Franklin could move, she could be saved. On the flight deck, Commander Jericho and his damage control teams had fashioned a water barrier at frame 110, approximately 400 feet from the bow. Using all available fire hoses, they constructed a curtain of spray between the forward section, requiring defense, and the aft fires they could not yet suppress. The water curtain, a safety feature designed into the Essex-class carrier, functioned precisely as intended. The spray wall dissipated radiant heat and suppressed smoke, providing a defensive perimeter the firefighting crews could maintain. Beyond that barrier, the forward flight deck remained substantially intact, but danger persisted. At Aero 45, one of the most violent secondary explosions erupted. A magazine containing 5-inch ammunition detonated beneath the hangar deck. The force was devastating. Observers on nearby destroyers believed Franklin had finally disintegrated. A column of flame shot 500 feet skyward, a towering inferno visible from 20 miles distant. The detonation claimed dozens of firefighters working in that area. It punched a hole spanning 3 decks from the hangar deck downward to the 3rd deck. Sharp fragments tore through previously undamaged spaces, igniting fresh fires and wounding additional personnel. Yet something extraordinary occurred. The structural walls surrounding the magazine, all manufactured from special treatment steel, absorbed most of the explosive force. In a differently constructed vessel, that explosion would have burst through standard steel bulkheads and spread devastation sideways, almost certainly breaking the ship's spine. Fragment projectiles would have penetrated adjacent compartments, detonating other ammunition stores in a cascading chain reaction. But the STS bulkheads, engineered to withstand fragmentation, channeled the blast upward and outward rather than laterally. The nearby magazines survived intact. Some fire main pipes in that section were severed, yet redundant systems in other areas continued supplying pressure. The ship recoiled from the blast, yet her frame endured. By 1000, roughly 2 hours and 52 minutes after the attack, Franklin was stabilizing. Flames were being contained, though not eliminated. The list had declined to 9 degrees through careful management of counter-flooding. The engineering plant was producing power for 4 knots, then 6, then 8. By midday, Franklin was cruising at 15 knots. The turnaround was extraordinary. A carrier that observers had watched dying was now moving at respectable velocity. Her fires largely managed, her crew reorganizing recovery efforts. By 1600, 8 hours after being struck, the principal fires were extinguished. Smoke continued billowing from damaged areas, and isolated fires periodically flared as crews discovered burning pockets. But the worst was finished. Franklin had made it through. The human cost was enormous. Based on latest research by naval historians, 807 personnel had been killed, the majority in those first 10 minutes. An additional 487 bore wounds, numerous suffering severe burns requiring extended medical care. More than 30% of her complement was dead or injured, yet she floated. She moved. She would reach safety. Captain Gerris directed the bow toward Ulithi Atoll, some 2,500 miles to the southeast. Franklin, accompanied by Pittsburgh and escort destroyers, commenced the lengthy voyage toward home. Her velocity reached 15 knots initially, though as the engineering crew completed repairs and reactivated boilers, she eventually achieved 25 knots. She would make it. The journey to Ulithi tested the structural concepts that Homer Lenoy Ferguson had advocated 5 years earlier. Franklin was essentially a floating ruin, barely seaworthy, tilted with massive holes penetrating deck and hull. Yet she remained buoyant because the design held. The hangar deck, subjected to fire temperatures reaching 2,000 degrees Fahrenheit, showed serious warping but no structural collapse. Support beams had bent from heat but had not fractured. The flight deck, perforated in 53 locations, still bore the load of firefighting apparatus and hundreds of personnel conducting temporary repairs. Hull plating, stressed by the list, explosions, and counter-flooding, kept the compartments sealed. Most impressively, the torpedo protection system, designed against underwater weapons but experiencing tremendous shock from internal blasts, remained functional. Not one vital bulkhead in the underwater protection system gave way. Franklin arrived at Ulithi on March 24th, 6 days after the attack. She anchored in the lagoon, bearing 807 fallen sailors. But she had arrived under her own power. Over 4 days, temporary repairs were conducted, primarily patching flight deck openings and securing the aft compartments for the transit to Pearl Harbor. On March 28th, Franklin departed Ulithi heading for Pearl Harbor, still achieving 20 knots despite the damage. She entered Pearl Harbor on April 3rd, creating tremendous reaction. News of her survival had circulated through naval ranks, but watching the damaged carrier steam into harbor under her own power remained startling. The Navy performed temporary repairs sufficient for passage through the Panama Canal and the subsequent Atlantic voyage. On April 10th, Franklin got underway from Pearl Harbor, heading for the Brooklyn Navy Yard in New York. She arrived there on April 28, 1945, nearly 6 weeks following the attack. At Brooklyn, naval engineers and Bureau of Ship specialists evaluated the full scope of destruction. War Damage Report number 56, compiled during subsequent months, detailed the catastrophe. The hangar deck had been obliterated across 40% of its expanse. The flight deck contained 53 holes, ranging from 3 feet to 20 feet across. Over 30% of crew living spaces were completely incinerated. Steel bulkheads warped by extreme heat, their contents reduced to charred remains. Millions of individual structural pieces required complete replacement. The ship's ventilation system needed a total overhaul from top to bottom. Every electrical circuit and power system had to be rebuilt from scratch. The destruction ran so deep that restoring the ship would consume at least 2 years and demand spending nearly equivalent to constructing an entirely new carrier from the keel up. Yet underneath all that carnage, the fundamental framework remained sound. Navy engineers who inspected the keel found it perfectly straight, within all acceptable tolerances. Despite the raging fires and tremendous explosions that had torn through her, the hull plating held together. The machinery compartments, though blackened by smoke and twisted by intense heat, could be repaired. The structural frames and support beams bore the marks of terrible stress, but showed no signs of breaking apart catastrophically. Franklin possessed the potential to be rebuilt. She never would be, because the war concluded before any major repairs started. Yet she absolutely could have been. The very fact that this possibility existed was extraordinary. The Navy had other plans for what came next with Franklin. She represented the most severely battered aircraft carrier to make it through the entire war, serving as a unique testing ground for understanding carrier resilience. Rather than rush into repairs, the Navy chose to study her intensely, treating her wreckage as a means to learn how carriers endure extreme battle conditions. For months on end, teams of engineers moved carefully through her damaged sections, taking measurements, shooting photographs, running tests on different materials and systems. They recorded how specially treated steel responded to extreme heat, charting exactly how much the structural pieces bent and what temperature zones existed during the inferno. They traced the path of the magazine blast and documented how the reinforced STS bulkheads had contained that terrible explosion. They examined how the multiple independent water systems for fighting fires had kept functioning even as huge portions of the ship lay in ruins. Every measurement, every observation was collected, studied carefully, and funneled into an enormous technical study that would shape the design of every carrier built after the conflict. Yet Franklin's survival offered just one confirmation of the Essex-class blueprint. The entire class demonstrated its worth repeatedly throughout the war's final months. USS Bunker Hill took direct hits from 2 kamikaze planes on May 11, 1945, near Okinawa, and the blows proved devastating. The attacks killed 396 sailors and injured 264 others. The 2 crashes happened just 30 seconds apart. The initial kamikaze struck planes that were being refueled on the flight deck, igniting massive fires that resembled Franklin's catastrophe. The second kamikaze punched through to lower compartments, pushing flames into enclosed areas. The ship's firefighting crews battled the blazes for nearly 5 solid hours before finally getting them under control. Bunker Hill endured the punishment and steamed back to port on her own power. Like Franklin, the damage was so extensive that she never entered service after the war, yet she stayed afloat. USS Intrepid experienced 4 separate kamikaze strikes throughout the conflict. She was struck on October 29, 1944, fixed up, and sailed back into action. November 25, 1944 brought another hit. The crew repaired the damage again. March 18, 1945 saw a third impact. Then came a fourth strike on April 16, 1945. Each time, the ship's sailors extinguished fires, made necessary repairs, and went straight back into the thick of battle. She outlasted the war and continued sailing for decades, remaining in service until 1974, serving 31 years total. Today she sits as a museum vessel in New York Harbor. USS Enterprise, called the Big E by her crews, became the aircraft carrier that absorbed the most bombing, torpedoes, and various combat damage during World War II, while still managing to survive. Bombs from battles at Eastern Solomons, Santa Cruz, and countless other engagements tore into her hull. She narrowly escaped being sunk by multiple kamikaze strikes in May of 1945. Every time, the Essex-class structure and state-of-the-art damage control kept her fighting. She made it through the war and continued operating until 1947. USS Hancock, USS Belleau Wood, USS Lexington, USS Wasp, USS Yorktown, USS Randolph all absorbed tremendous battle damage, yet remained afloat. The connecting factor was Essex-class engineering. The careful deployment of special treatment steel, the intricate internal divisions separating compartments, the overlapping firefighting networks, the meticulous engineering that ensured every part of the ship worked together for survival. Every single one of these carriers stayed off the ocean floor, none was written off as a total loss, all returned home. This outcome resulted from superior design and engineering, not fortune. The comparison with other carrier designs revealed stark contrasts that history recorded thoroughly. The British armoured carriers, which many naval strategists had believed would outsurvive American vessels, actually proved more fragile in actual combat. Their armoured flight decks, made from 3-inch thick armour plating, stopped bombs from penetrating down to the hangars. However, when flames began in the hangar for any reason, fighting those fires became agonizingly difficult because the solid armour above and around the hangar space acted like an enclosed furnace, trapping superheated air and smoke inside. The ventilation couldn't manage the intense heat, firefighters couldn't function in such brutal conditions, and battle injuries that an Essex carrier could have ready within days left British ships sidelined for weeks. HMS Formidable was struck by kamikazes twice in 1945. Although the armoured deck protected against penetration, burning fuel from the crashing aircraft set fires inside the hangar that forced the ship to withdraw from combat both occasions. HMS Illustrious found itself repeatedly removed from action by damage levels that Essex crews would have considered manageable. HMS Victorious, HMS Indomitable, they all ran into comparable troubles. The British carriers possessed ruggedness, but their armour-first philosophy created rigidity, reduced adaptability, and left them vulnerable to mission failure despite surviving direct strikes. The Japanese fleet carriers, which opened the conflict with some of the globe's finest designs, suffered from fundamental limitations baked in by international treaty rules and inexperience in real combat situations. At Midway in June of 1942, 4 Japanese fleet carriers went under when bombs struck them, impacts that an Essex design would quite likely have endured. Akagi, Kaga, Soryu, and Hiryu all sank after taking 1,000-pound bomb hits that punched into their hangars and detonated fuel and ammunition. The Japanese carriers had weak compartmentalization, primitive firefighting equipment beside American standards, and almost no structural armor protection. They functioned as floating powder kegs. Once explosions cascaded through the ship, no system existed to stop the destruction. By 1945, Japan fielded no functional fleet carriers for sustained operations, while America had 20 Essex-class carriers actively deployed throughout the Pacific. The performance statistics of the Essex class validate Ferguson's genius with unmistakable power. 24 ships were constructed in this class. 14 entered actual combat in the Pacific War. These ships absorbed a combined total of 39 bomb hits, torpedo strikes, and kamikaze attacks. The casualty count totaled over 2,600 killed across the entire class. 0 sank. None were abandoned as total losses beyond repair. Every damaged Essex ship was restored and returned to fighting except Franklin and Bunker Hill, which remained in reserve after hostilities ended because urgent repairs weren't necessary. The class accumulated a total of 143 battle stars collectively. They participated in every major Pacific operation from Tarawa through Tokyo Bay. Yet what of the genius architect of this revolutionary design? Homer Leroy Ferguson entered the world in Waynesville, North Carolina on March 6, 1873. At just 15 years old, he entered the United States Naval Academy at Annapolis, remarkably young even by the standards of that time. He completed his studies in 1892, finishing at or near the very top of his class, though sources conflict about whether he ranked first or third. The historical record is unclear on this detail. What remains certain is that he graduated with distinction and received immediate selection for specialized advanced training. Instead of proceeding directly to sea duty, he received assignment to Glasgow University in Scotland from 1892 to 1895, where he studied naval architecture and engineering from legendary Scottish ship designers who dominated the field globally. Glasgow throughout the 1890s represented the undisputed center of worldwide shipbuilding. Ships built in Scottish shipyards were among the speediest and most sophisticated vessels anywhere. Ferguson learned from professors who had engineered fast blockade runners for the Confederacy during America's Civil War, vessels that employed iron frames and revolutionary hull shapes. He absorbed knowledge in stress calculations, water dynamics, material science, and the principles that made ships structurally sound. He internalized the Scottish tradition, emphasizing that vessels must be constructed to endure, prioritizing survival ahead of mere speed or firepower. His instructors drilled this concept home repeatedly. A sunken ship accomplishes nothing. Build ships that last. Ferguson came back to America in 1895 and launched his professional life as a naval constructor. He served at ironworks in Baltimore, later at Navy facilities in Portland, Bremerton, and Bath. He oversaw the construction of major warships, gaining real-world understanding of the differences between drawings and finished vessels. In 1902, he joined the team at Newport News Shipbuilding, then a modest operation in Virginia established by railroad tycoon Collis P. Huntington back in 1886. Ferguson started as deputy head of construction operations. His technical brilliance and natural leadership showed immediately. By 1905, at just 32, Ferguson walked away from his Navy position, taking permanent civilian employment with Newport News full-time. His advancement through the company ranks proceeded swiftly. By 1914, he had attained vice president rank under company president Albert Lloyd Hopkins. On May 7, 1915, Hopkins boarded the ocean liner RMS Lusitania for a business voyage to England, traveling to handle shipyard matters. A German U-boat sent a torpedo into the vessel off Ireland's coast. The liner went down, taking Hopkins with it, among 1,198 souls lost that day. Ferguson, who had appeared destined to eventually take over from Hopkins, abruptly found himself facing leadership demands. On July 22, 1915, Ferguson, now 42 years old, stepped into the role of president at Newport News Shipbuilding. He occupied this position for the following 31 years, stewarding the company through the First World War, the economic devastation of the Great Depression, and the Second World War. Ferguson's stewardship transformed Newport News into the nation's finest naval shipbuilding facility. Under his leadership, the yard constructed 7 of the 16 battleships in Theodore Roosevelt's Great White Fleet that circled the globe from 1907 to 1909. Throughout World War I, Ferguson orchestrated intensive shipbuilding efforts that produced 25 destroyers for Navy deployment. Beyond that, he championed innovative programs supporting worker welfare and living conditions. In 1918, recognizing that shipyard employees needed housing, Ferguson collaborated with federal authorities to establish Hilton Village, one of America's earliest planned residential communities. He gave official status to Newport News training program for young workers in 1919, establishing a structured apprenticeship that became a template for technical training across the nation. That same apprenticeship program continues operating presently, preparing upcoming generations of ship construction specialists. Nevertheless, Ferguson's greatest achievement arrived in the late 1930s, as international tensions escalated. Navy leadership began designing a fresh generation of aircraft carriers meant to supersede the restricted designs from the prior decade. What would become known as the Essex class would form the foundation of America's future naval air strength. Ferguson recognized this moment as his chance to revolutionize how warships were engineered. He possessed a visionary concept: integrate protective armor directly into structural design. In conventional naval engineering, armor functioned as supplementary protective covering, bolted onto the hull structure. Armor provided defense, but added no structural contribution. Ferguson proposed an entirely different approach. What if protective armor actually became part of the load-bearing framework? If you incorporated special treatment steel throughout the whole vessel, every steel plate would simultaneously strengthen the ship and deflect weapons. Special treatment steel had been invented by Carnegie Steel in the early 1900s. This nickel-chromium steel combination possessed extraordinary characteristics. It offered protective qualities matching Class B armor plating, defending against shrapnel, bomb splinters, and fragmentation effectively. However, unlike conventional armor plate, STS remained flexible enough for standard shipbuilding techniques. You could bend it, weld it, shape it into complicated configurations. It performed like standard structural steel carrying loads. The breakthrough was adaptability. You could deploy it anywhere a ship needed strength. The challenge came down to economics. STS commanded premium pricing, costing roughly 30% more than conventional steel. Equipping an Essex carrier totally with STS would exceed Navy budget limitations significantly. The Bureau of Ships rejected Ferguson's suggestions as fiscally unrealistic. Ferguson provided hard numbers to dispute them. An Essex carrier constructed entirely with STS would weigh less than a conventional design because protective qualities merged with structural strength. That weight savings meant increased capacity for aircraft, additional fuel reserves, and greater ammunition storage without increasing overall displacement. Furthermore, the built-in redundancy created through armor-grade steel everywhere implied that strikes destroying standard carriers might leave this ship operational. You'd spend more building it, Ferguson acknowledged, but you'd preserve sailors' lives in battle and possibly preserve the entire vessel. Ferguson had supporters in high places. Naval officers recalling early war carrier losses knew survival eclipsed all other considerations. USS Lexington sank at Coral Sea in May 1942, not from the initial Japanese torpedo blows, but from internal explosions triggered by ruptured fuel systems that ignited hours afterward. USS Yorktown, wounded at Coral Sea, got temporarily repaired in just 2 days at Pearl Harbor and rushed back for Midway fighting. She absorbed multiple bomb and torpedo strikes at Midway, nearly made it back to port, but ultimately went down from a submarine's torpedo while being towed home. Both ships possibly would have lived through better damage control and structural toughness. Navy officials endorsed Ferguson's blueprint with certain adjustments. The hangar deck armor thickness became 2.5 inches of STS instead of the originally suggested 1.5 inches. Beneath it, the lowest hangar compartment deck measured 1.5 inches STS. The flight deck rested upon a skeleton of STS I-beams. The waterline protection used 4-inch Class B armor with STS support behind it. Throughout the interior, STS formed bulkheads wherever feasible. The torpedo defense structure, that intricate compartment network absorbing torpedo effects, incorporated heavy STS walls for the ultimate barrier holding back the ocean. Across each Essex-class carrier, thousands upon thousands of tons of special treatment steel went into construction. Exact tonnage differed between ships and remains unclear in publicly available records, though engineering analyses estimated somewhere between 3,000 and 4,000 tons per vessel. The expense proved enormous, producing a warship where every beam, every plate served the cause of survival. Ferguson championed innovations extending past simply deploying STS strategically. The Essex class featured compartmentalization beyond anything previously achieved in carrier construction. Earlier carrier designs emphasized spacious open areas for operational convenience. Ferguson demanded the reverse. Subdivide ruthlessly, transform every passageway into a potential barrier against flames. The Essex carriers incorporated compartmentalization on an extraordinary scale, featuring hundreds of isolated sections that could each be independently sealed, flooded, or open to ventilation. The precise compartment count remains unspecified in existing documentation, though the design intent was unmistakable. Losing several compartments shouldn't endanger buoyancy or equilibrium. The firefighting apparatus represented entirely new thinking. The Essex-class carriers broke away from traditional fire suppression design in fundamental ways. Instead of the single fire main that ran the length of older ships, a catastrophic vulnerability if damaged, Ferguson envisioned something revolutionary. He created multiple independent fire mains, each supplied by separate pumps stationed throughout different engine rooms. Through an intricate network of valves, these systems could be cross-connected or completely isolated, ensuring that damage to one section wouldn't cripple the entire ship's firefighting ability. 9 separate fire pumps formed the heart of this redundancy. Each could push thousands of gallons per minute through the system. If one section of piping was severed, water could be rerouted through alternative paths. If pumps were damaged or failed, others stood ready to compensate. The philosophy was simple but revolutionary. Assume everything would break, then make sure the ship survived anyway. The hangar deck posed unique dangers. Ferguson designed overhead sprinkler systems, capable of drenching the entire space with seawater in moments. Fire and smoke barriers could be created using water curtains. Carbon dioxide flooding systems could flood fuel storage areas, smothering flames before they spread. Emergency ventilation allowed spaces to be pressurized to keep smoke out or vented to clear it away. Every single system carried multiple backups, reflecting Ferguson's core conviction that redundancy wasn't luxury, it was necessity. The first Essex-class carrier, USS Essex CV-9, was laid down on April 28, 1941, at Newport News Shipbuilding. Ferguson's yard led the entire class construction effort. Remarkably, the ship was completed in just 20 months, commissioned on December 31, 1942. USS Yorktown CV-10, built to honor the carrier lost at Midway, was laid down on December 1, 1941. Her keel went down just 6 days before Pearl Harbor struck. She entered service on April 15, 1943, under the command of Captain Joseph J. Clark. USS Franklin CV-13 was laid down at Newport News on December 7, 1942, exactly 1 year after Pearl Harbor. She was launched on October 14, 1943, with Lieutenant Commander Mildred H. McAfee, director of the Waves Women's Naval Reserve, serving as sponsor. Franklin was commissioned on January 31, 1944. Yet when these vessels first steamed into the Pacific in 1943, Ferguson's innovations remained untested in actual combat. They existed as theories, calculations, design decisions made in drawing offices and fabrication shops, far removed from the reality of warfare. The ships looked formidable, certainly, but would they truly endure when battle tested them? The answer emerged across battles throughout 1943, 1944, and 1945. They endured. Kamikazes that would have sent earlier carriers to the bottom left these ships afloat. Fires that raged through their hangar decks were contained by damage control systems that functioned exactly as designed. Bombs that penetrated their flight decks were stopped by compartmentalization that prevented destruction from spreading. The Essex class became the most successful aircraft carrier design ever built, precisely because Homer Ferguson had built ships engineered to survive. Ferguson remained president of Newport News Shipbuilding until July 31, 1946. At 73, he watched his carriers prove themselves against every test combat presented. After stepping down, he remained deeply involved in Newport News. He played a crucial role founding the Mariners Museum alongside Anna Hyatt Huntington and her husband, Archer M. Huntington. He served on the museum board, helping build collections that documented shipbuilding and maritime history. He died on March 14, 1953, just 7 days after turning 80. Ferguson received no Medal of Honor, no Navy Cross, no official congressional recognition. His name adorned no warships. The general public never knew who he was. His contributions were too technical, too distant from the drama of combat, too abstract to capture popular attention. But Franklin's survivors never forgot. Decades after the war ended, they organized reunions to preserve their shared experience. The first gathering occurred in 1947 in New York City, with roughly 200 men present. They talked, remembered those lost, and marveled that they had survived at all. These reunions continued year after year, later spacing to every few years as the men aged. The numbers dwindled as survivors passed away, but the bonds persisted. On the 50-year anniversary in 1995, about 80 survivors gathered in Charleston, South Carolina. They visited the USS Yorktown Museum, an Essex-class sister ship to Franklin. Walking those decks, they saw the compartments, traced the fire mains, examined structural details. Understanding deepened in ways it never had during their service aboard Franklin. The STS bulkheads, the multiple fire mains, the compartmentalization, all the engineering decisions that had kept them alive became tangible and visible. In 2005, 60 years after the attack, fewer than 30 survivors attended what would be the final official reunion in Norfolk, Virginia, just miles from Newport News. The shipyard arranged a tour. These men, now in their 80s, walked through modern shipyards where nuclear carriers were being constructed. They observed computer design stations, robotic welding systems, advanced materials. Yet the fundamental philosophy remained unchanged: build ships that survive. The young workers, continuing Homer Ferguson's tradition, heard a simple message from these elderly visitors. We're alive because men like you built our ship right. Build these ships right too. Someday men you'll never meet will owe you their lives. It was the essential truth of everything they had experienced. Engineering excellence translated into lives saved. Every Franklin survivor owed his survival to choices made in offices and shops years before war began. Decisions about steel thickness, bulkhead positioning, fire main routing, compartment design. The chaplain fighting fires, the engineer keeping engines running, the navigator coordinating damage control, all were enabled by their ship's design. Without Ferguson's innovations, their courage would have meant nothing. Franklin would have sunk, and 800 deaths would have become 2,500. The Medal of Honor recipients aboard Franklin embodied the human dimension of the ship's survival. Lieutenant Commander Joseph Timothy O'Callaghan received the Medal of Honor, the only chaplain in naval history to achieve this distinction. His citation described how he courageously led men in fighting fires and battling damage. He entered burning compartments alive with exploding ammunition and threatening flames, leading teams below to rescue lives. His courage and cool leadership became the crew's rallying point. After the war, O'Callaghan taught mathematics and physics at Holy Cross College in Worcester, Massachusetts, serving as physics department head. He rarely spoke publicly about his Medal of Honor, dying in 1964 at age 62. His autobiography, I Was Chaplain on the Franklin, published in 1956, remains among the finest accounts of the attack. Lieutenant Junior Grade Donald Arthur Gary received the Medal of Honor for engineering space heroics. He organized and led firefighting parties to the hangar deck and entered fire rooms to raise steam in one boiler. His actions risked his life while helping prevent the ship's loss. After the war, Gary left the Navy and worked as an engineer for Ohio Edison, a power company, until retirement. In 1960, a young naval officer wrote asking for damage control advice. Gary responded with detailed technical instructions and offered this wisdom: remember that systems don't fail, people fail. If you design systems with enough redundancy, enough backup, enough alternative paths, then when people reach their limit, exhausted and terrified and ready to surrender, the ship will carry them. Build that kind of ship. Gary died in 1977 at age 56. Commander Stephen Jerker Jr., the navigator who organized flight deck damage control, received the Navy Cross. He continued his naval career after the war, retiring as a captain. His Franklin experience shaped his later work in damage control training. He died in 1993 at age 83. Captain Leslie E. Geitz remained controversial. His strict discipline and autocratic command style had made him unpopular before the attack. After the disaster, he faced allegations that he accused men who abandoned ship of desertion, despite many being ordered overboard or jumping to escape certain death from fire. A Navy investigation found no wrongdoing, concluding that communications broke down in the chaos. Some men genuinely believed abandoned ship had been ordered. Others jumped to save themselves. Geitz was promoted to Rear Admiral, but the controversy persisted. He retired in 1946 and died in 1975, largely forgotten. Yet naval historians studying Franklin's survival noted something crucial. His refusal to give up, his determination to keep the ship moving, his pushing of the crew beyond normal limits. These decisions validated her survival. Without engineering capability to survive combined with command determination to save the ship, Franklin would have been lost. Franklin's post-war years bore little resemblance to her wartime service. She arrived in Brooklyn in April 1945 and remained there through the war's end. When Japan surrendered in August 1945, repairs never began. With the war over and no immediate need for her massive restoration, the Navy deemed the costs unjustifiable. Franklin was decommissioned on February 17, 1947, and placed in the reserve fleet at Bayonne, New Jersey. She sat there for nearly 20 years, a dying ship slowly falling apart. The Navy redesignated her CVA-13 as an attack carrier in 1952, then CVS-13 as an anti-submarine carrier in 1959, and finally AVT-8 as an aircraft transport in 1961-1963. These were merely administrative changes on paper. Franklin never left the reserve fleet. She remained too damaged, and modernization costs were deemed wasteful when newer carriers existed. In 1964, Franklin was struck from the Naval Vessel Register. In May 1966, she was sold to Peck Iron and Metal Company in Portsmouth, Virginia, for $228,000. But the Navy repossessed her in June 1966, needing her 4 turbo generators urgently for other vessels. On July 27, 1966, she was sold once more to Portsmouth Salvage Company in Chesapeake, Virginia for scrapping. On August 1, 1966, tugs began towing Franklin from her berth for the last time. As she moved down the channel toward the scrapyard, a Coast Guard cutter passed by. It rendered honors with 3 short whistle blasts, a naval tradition of respect. The cutter's captain, a World War II veteran, later explained his decision. That ship earned honors. I didn't care what orders said, she deserved respect. It was the last salute Franklin received. Over the following months, she was dismantled. Her steel, including the thousands of tons of special treatment metal that had saved her, was recycled into new construction. According to naval legend, though never officially confirmed, some of that steel went into USS Enterprise CVN-65, the first nuclear-powered aircraft carrier, commissioned in 1961. Enterprise served 51 years, the longest active service life of any aircraft carrier in history. When finally inactivated in 2012, naval historians noted that her survivability features, extensive compartmentalization and redundant systems, traced their lineage directly back to Essex-class design principles. The ship that refused to die had taught the Navy how to build ships that wouldn't need to prove their toughness through combat. Today, researchers at the Naval History and Heritage Command in Washington, D.C., can examine War Damage Report No. 56, the official technical analysis of Franklin's damage and survival. Over 300 pages of technical analysis, photographs, and diagrams, it remains classified as restricted. Not because it reveals modern carrier information, but because the damage control techniques it describes remain so effective that the Navy considers them operationally sensitive. Every damage control school in the Navy uses Franklin's survival as a case study. Every naval architect designing combat ships studies how her structure withstood impossible conditions. Every carrier officer planning operations understands their confidence in operating close to enemy shores rests on knowledge that their ship is designed to survive. Franklin's lessons extend far beyond naval warfare. In any field where human lives depend on engineering, the same principles apply. Design for worst-case scenarios, build in redundancy, use the best available materials, even when they cost more. Create systems that don't fail catastrophically, that degrade gracefully, that give people time to react and recover. Homer Ferguson applied these principles to aircraft carriers in 1940. They apply equally to airliners, spacecraft, earthquake zone buildings, any human artifact where failure means death. The attack on Franklin killed 807 men in 30 minutes. The ship's survival saved approximately 1,700 more. That ratio, more than 2 lives saved for everyone lost, represents the return on engineering excellence. The expensive steel, extra compartments, redundant systems cost money, time, and effort during construction, but they purchased 1,700 lives in combat. No one can calculate what those men contributed in the decades following. How many children they raised, how many businesses they built, how many students they taught, how many lives they touched. Ripples from their survival spread across generations, impossible to quantify, yet undeniably real. Franklin's story ultimately concerns the invisible victory, the triumph occurring before battle, in drawing offices and shipyards where engineers and architects made decisions determining whether men would live or die years later. These decisions lack combat drama. No one receives medals for specifying thicker bulkheads. No one becomes a hero for insisting on redundant fire mains. But these decisions matter as much as courage under fire, perhaps more because they enable courage to succeed. Homer Ferguson never received a Medal of Honor for designing ships that saved thousands of lives. He never appeared in newsreels or history books as a hero. His contribution was too technical, too abstract, too distant from smoke and fire. But Franklin's men knew. The 1,300 who walked off that burning ship alive, who went home to families and futures, who lived long lives because their ship refused to die. They knew. Somewhere in the chain of decisions from conception through construction, someone had made right choices. Someone had insisted on extra steel, additional compartments, redundant systems. Someone had believed men's lives were worth the expense. On March 19, 1945, off Japan's coast, those decisions proved more valuable than all the courage and sacrifice combined. Because courage without tools is martyrdom. Sacrifice without capability is waste. Heroism without support is tragedy. But when brave men serve in ships built by capable engineers, when sacrifice is enabled by superior design, when heroism is supported by thoughtful planning, then victory becomes possible. Franklin proved this at terrible cost, then brought 1,700 witnesses home to testify to its truth. The ship that shouldn't have survived became the ship that proved survival possible, validating every decision that went into her construction.